motivation. The goal of the project will be to find heat capacity of the two-dimensional lattice of transition metals, which are, it is a objectively existing chemical substance with some useful properties. Many interacting spins on the transition metals are quite challenging. And the reason why we are going to do a project, because it is not doable by pen and paper. So it's not, I can mumble something and do approximate solutions. And I believe Professor Brookhouse was telling to some approximate methods. But literally, exact answer is not available for multiple. But if you take only one metal with one unpaired spin, and for the math, it doesn't matter whether it is spin on the ruthenium atom or it is nuclear spin from NMR experiment, the mass will be the same. So again, I was not checking your happiness and fluency with quantum part of physical chemistry, but I think I want to believe that you all are happy with the concept of spin, up and down. And the main difference between quantum hemisphere of brain of a theorist and statistical and thermodynamical that in statistical and thermodynamical approach, there is no much dynamics. So typically systems come to equilibrium. And equilibrium often means that the system of an interest is placed on a thermostat. And some people put a humoristic view of it, and it is even reflected in common terminology and used in the textbooks. So if a system, and it is a like colloquial language in theory community, if a system is placed on a thermostat, one often tells that the system is in a bath. So if you are looking on a spin, we can tell that the spin is in a bath. Okay, so the spin itself can have only two states, up and down, right? And it is a main difference from translational, rotational, from degrees of freedom in classical sense, right? So there is nothing else. And on one hand, it challenges our common sense human thinking, but on another, it is the simplest possible mathematical problem. So here is the general formulation of a problem. So if you have bath of a temperature T, and we know what is the energy of spin in state up, and we know what is the energy for spin in state down, what will be the energy of the spin if it is in the equilibrium with the bath? So, and I hope to answer it within next, whatever, 40, 50 minutes. So find energy of this two-level system as a function of temperature. And the homework that I'm inviting you to try is to take the answer from whatever we will get in 40 minutes and apply derivative, just to find heat capacity as derivative over temperature of the answer from today's in-class material. So basically, you just take one derivative over temperature and you're done. Well, plus some verbal explanation. Yeah, it's not a trap, but basically, basically you can answer at which temperature there is a minimum, there is maximum, and how do you interpret? Like some freestyle comments. Okay, let's see how I'm going with the. So this one was figure 1. So we are done with motivation, figure 1, and goals. So I'm going to show you expected outcome and mumble a little bit what it is, how do we interpret it, and I'm going to erase it, right? It's one of the reasons why we are meeting face to face. It's hard to mimic this sound in pure online. So I need energy as function of temperature, or I can put Boltzmann constant in front if we are just looking for qualitative trends. It doesn't matter, temperature or temperature times Boltzmann constant. And before I will, so my plan is to practice same style as like calculus and differential equations good lecturers do. I'll try to pretend. And typically in math, there is a common practice to declare the answer and then discuss it, and only then spend boring time on proving it. So that if you don't care about proof, you can fall asleep and relax. At least that it is what I was doing in undergraduate time. So you are already aware of Boltzmann distribution. So if one knows the energy and temperature, how does it enter? How does Boltzmann factor looks like? How temperature enters Boltzmann distribution? In which form? Crystal?
Kelvin?
Huh?
Kelvin?
In which mathematical form? Like, does Boltzmann includes temperature squared or cosine of temperature?
No, it's e to the temperature, like it's in an exponent.
So e to the temperature or e to the inverse temperature?
Oh, inverse temperature.
Inverse temperature. Okay, yeah, thank you. Everyone agrees? So just for mathematical comfort, I will put another axis and put here, so blue will be temperature and red will be minus inverse temperature. And for mathematical comfort, I can put also some constants here, like Boltzmann there, and some mu and b, which I'll define later on there, but mainly it's inverse temperature. So they behave oppositely, right? So when temperature is 0, the minus inverse temperature will be minus infinity, right? When temperature is equal to constant, like the inverse temperature will be -1. So we can find such constants. When temperature equals infinity, the minus inverse temperature will be 0, right? So I'm going to plot the answer of our today's discussion in this axis. And I'm not well prepared and carrying my memory because most of the answer will be negative. I didn't left enough space. So the answer will look this way. And here I do not care what it is, because we cannot have temperature bigger than infinity. But we can have inverse temperature go to positive values, and some mathematical functions are defined there. So something crazy happens for the another half of the plane, and we are not going to consider it in the subject of thermodynamics, but in negative temperatures correspond to lasers when Boltzmann is violated. Not Boltzmann, but Boltzmann distribution. So when temperature is 0, the energy will be minus mu b, and I'm going to define all things. And when temperature is infinity, the total energy of the spin in a bath will be 0. And as we progress from 0 temperature to infinity, it will the overall energy will increase. So how to interpret it, and what does it mean? If we have two levels, one level for spin down and another for spin up, for example, then when it is in equilibrium, when temperature is 0, with 100% probability, we are on the lowest level, right? If we go to temperature some constant value, then we can arrive to distribution of probability to be up and down, and average energy will be somewhere in between them, midway. Oh, hi, how are you? That's okay, that's okay. So it will be midway. And if you have temperature equals infinity, no. Here it will be like, so no one took the chance to correct me. I was lying here. It will be majority on the lower, but something will be thermally promoted to the up. And when temperature is infinity, it is 50-50. And therefore, if energies of the lowest and highest state are positive and negative, they will compensate each other and arrive to 0. Okay? So the practical goal for me, for my exercises here, is to provide mathematical function for this. So energy as function of temperature, it will be something like minus mu b hyperbolic tangent of mu b over temperature. And your homework will be nothing but take derivative. Some of you may even complete homework even before lecture ends, plus some verbal analysis. So before I go to boring details, let's discuss if you have any, let us say, protests, questions, corrections, or requests for clarifications.
I have a question.
Yes, Sohi.
What is the mu stands for?
Mu stands for gyromagnetic ratio. We will place our two-level system in magnetic field with Zeeman splitting. Any other? So does it look reasonable, or you can just show yes, very bad, or additional things are needed? Can you? Okay, and online? Okay, mostly yes, but some clarification is needed. So what is the challenge? Why it is needed in wet chemistry labs to control transformation of reaction? Sometimes you can track if reaction protest or not by measuring response of the system to heating, and by looking on the heat capacity, one can identify whether it is one or another tabulated chemical, something like that, right? Here we are going to check for heat capacity as a signature of this one spin in the bath. The challenge, the interesting consideration will be when in the project, and I'll start maybe when we have another lecture on Monday, when we have several spins and they interact with each other. But as a reference point, we need to see how temperature increases probability of spin to be flipped up, at least to some percent, and give quantification, quantitative measures of this equilibrium states. Okay, so if I arrive by this equation and this line by the end of the meeting, I will be very happy. Do you let me go? I mean, not depart the room, but let's go forward. Okay, then I'm going to erase the stuff, and we are done with expected outcome and figure 2 and homework 1. So now we need to go to definitions. So if we have spin in magnetic field, what is the energy? It just if the spin is along the field is one energy, if it is against it is another. And we have the magnetic field and we have the gyromagnetic ratio, right? Any corrections or it is fine? Crystal? Okay. So the expert in NMR approves this equation. Now, if we consider, and we can put here the actual value of a spin, but if we, instead of quantum operators, we just look on the possible states, up and down, there will be, we can tell E sub E, where E sub I, where I is 1 or 2, or plus and minus, and then it will be two values, plus mu b or minus mu b, right? And it is Zeeman splitting. So this, if we increase magnetic field, then this energies E minus E plus will split proportionally to the magnetic field, right? So it is what in NMR experiment you have parallel and transversal fields. One is static that defines the splitting of the levels, and another is oscillating in radio frequency that induces transitions, right? So we do have energies. Now, what is the probability to find our two-level system in state number 1 for, let's say, spin 1? How do we find it, and how do we implement the concept of partition function? So we can introduce the, I'll answer it later, generally for state I, we do have a weight, right, which will be proportional to probability. And it is nothing but e to the power minus energy of state I divided by Boltzmann temperature. Please show me if you are seeing this equation every day and happy with it, or if you see it for the, oh, just Raise hands if you see this equation for the first time. And it will be not directed against anyone. Just tell me if you're not comfortable. Or let's do standard. Yes, if everyone is happy. No, if not happy, and in the middle. Okay, okay, yeah, thank you. Now the normalization or partition function. Partition function. So it will be partition function, or in some languages it's in the previous part of the course, which letter did you use for partition function, Q or Z? Capital Q. Because of maybe quotient. In some literature they call it letter Z, and it originates from German word Zustand summation, summation over states. So Q equals Z equals summation over such W weights over all available states, right? And then the next thing will be actual probability. So probability of state number I sub I will be weight of the state I divided by this Q or Z divided by statistical sum. And if someone is not comfortable with this abbreviations and notations, one can write explicitly e to the power minus energy of state I divided by kT divided by summation of such Boltzmann factors minus EI over kT for all possible values of energy. Okay? Now, there is one common general equation left. And I believe when you guys were giving me a little exam at our first meeting, when you were checking my knowledge about your exam for the first part, it was one of the questions, how to find an expectation value of an observable. Do you remember this? Okay, so if you have an observable, which can be like anything, can be magnetization, can be energy, can be some other things. So how to find expectation value? And the general way is to eigenvalue corresponding to eigenstate I times probability that this eigenstate is occupied, right? And it is more statistical approach rather than quantum. In quantum, there are like expression with wave functions, but in statistical is this one. And this P comes from here, right? Everyone agrees? Okay, now we are going to make a practical example. I want to apply this general definitions for the purpose to find expectation value of energy of the spin that takes the bus, spin on the thermostat. So I need only energy, right? So for the P sub I will plug in these values. For E sub I will use either this or that in magnetic field. And for instead of A, I will put letter E here and there, right? So no one is going to forbid me to do this. So expectation value of energy will be summation, and summation means I just add together. So first term, energy of state 1 times probability of state 1, and I will intentionally write it down in like slowly, step by step, so that we do not miss anything. Divide by statistical sum, or how do you, I will use statistical sum, but you use partition function, right? So which will be, let's yeah, z. Oh no, if I put probability, it already includes statistics, right? Plus E2 times P2. Now let's open what is this P1, P2. So E1 times, so I open it as, I'll do it slowly, weight of state 1 divided by weight of state 1 plus weight of state 2, where these weights are Boltzmann factors and depend on temperature, plus energy of state 2, weight of state 2, divide by weight 1 plus weight 2, right? Okay. I'll count a little time interval and then erase the board to have chance to write somewhere. Can I go forward? Okay, thank you. So I'll leave maybe the last one and then erase everything else. So I'm going to practice plugging in everything I know about. So instead of E1, I will plug yes, mu times B. Should I put minus? Okay. And then for weight 1, I will put e to the minus mu B divided by kt, right? And take your chance to find me lying, not intentionally. I can get scrambled with this minuses, but if you set up that energy is negative, then here you have negative energy and with minus from Boltzmann definition. Divide by e to the minus mu B kt plus another thing. And second portion will be plus mu B, right? Because of Zeeman splitting. And then the Boltzmann factor will be minus mu B divided by kt. And here we have same thing, but without energy. Minus mu B divided by kt, right? Do you, and in some sense I'm done, but it is very boring and not comfortable for analysis. Any protests or questions about this equation? Or it seems just natural plugging in terms and factors? Okay, so is there a way to simplify this expression? Would you allow me to take mu times b out of brackets? and inside the brackets we'll have e to the power mu b kt. Now, if I put it without my, maybe I'll put minus mu b, so that first term will be this way, and then I put minus e minus mu b kt. Catch me if you can. I'm not intending to make errors, but I can easily do several. Okay, and in the denominator we will have e mu b kt plus e minus mu b kt. So again, this is already the answer. It shows how the energy depends on temperature. And if we look for, if you plug in the value of temperature equals 0, we will get the fraction of one infinity divided by another infinity. So this everything here will be 1 times minus. We will get the first point on the dependence here, minus mu b. So one can see it, but it is kind of boring and uncomfortable. The brain will boil if trying to analyze it in this form. So let's just discuss this equation. If you see any symmetry, any simplification, any ways to analyze it. So, and any connection to the Wikipedia link that I sent you this morning. Huh? Oh, do the log. Okay. Logarithm can erase exponential. Okay. So one option is do the log. Do the log. Okay. Any other ideas we'll discuss? So it's not a scientific question. It's only a question of mathematical comfort. How to analyze these dependencies in more intuitive way. Okay.
Convert. I'm not sure it's right, but convert e to the mu b over kt changed to x.
Okay.
So then which makes tangent h. What is it? Cotangent.
Okay. Yeah. Yes.
Yeah.
Yes. This one will make our life really comfortable. Thank you. Thank you, Sophie. So minus mu b e x minus e minus x divided by e x plus e times x, e to the power x. Yes. But I don't know, maybe you are not picky, but I still feel discomfort. It's not the stuff that I'm doing every day in my head, processing several exponentials. Yes, thank you. John plus 1. So please keep tracking and saving me from errors. How are we doing with time? 56. Yep. Basically, we are done, but I'll spend time on drawing and explaining this stuff. So, and I'll briefly cover a little, how to say. Exactly. It is what I was going to say. Yes. So, what is Euler equation for regular? Yes. right?
Mhm.
And then one can, if one puts minus, and then by adding or subtracting this stuff, one is getting cosine phi equals e to the power I phi plus e I minus I phi divided by 2, and sine phi equals e I phi minus e minus I phi divided by 2i. Is it something that you practice every day? Come on, it's most pleasant equations in the undergraduate math. I'm not lying. I was so happy to learn about these equations. In high school, I was tortured by teachers and all my classmates too by practicing the cosine of double arguments, product of sines and cosines. And it is not possible for a human to memorize all of them. But if one takes this definition, one can derive all of these equations at once. So it is quite comfortable equation. But we are not going to use it today. We are taking it only as a reference and an example, so that if one takes Euler definition of regular trigonometric functions and just removes imaginary part here and there, here and there, then it will be definitions of a little bit exotic analogs of trigonometric functions, hyperbolic sine and hyperbolic cosine. And for hyperbolic sine and trigonometric functions, a lot of properties are very analogous. So multiplications of these functions, function of double argument, differentiating, like if one differentiates cosine, one gets sine. If one differentiates sine, one gets cosine, right? And so basically, everything we know for trigonometric function is immediately transformed to here with very minor changes. So if and yeah, no, I here. So if you take this definition, then one can write this equation minus mu b sine hyperbolic of x divided by cosine hyperbolic of x, or minus mu b tangent hyperbolic of x. And your homework will be just to take derivative of that, right? But we are not done. I am going to take an effort to draw this function and show how to plot function without a computer. I know it is a little exotic activity. It's hard to imagine that we all are on the inhabited island without calculators and computers, but just in case, preparing. So we are done with everything, and we are going to graphical analysis. And I hope it will take, and we are already done with hyperbolic functions. So do you allow me to erase the board? Okay. And I'll probably keep this results in case if I cannot count on my memory. So yes,
I have a quick question.
please.
So from okay, so like E equal minus mu b sine hx divided by cosine hx. Then when it converted to tangent,
Yes.
where is the minus should be disappeared? Or
Because, no. Minus is here.
okay.
Thank you.
Yep, that was my question.
And sine by cosine is a tangent.
Tangent. Yep.
Okay. So do you have any urgent appointments in like quicker than 20 minutes? Okay, then I'll promise to be done in 20 minutes and hopefully earlier. So I'm going to make a table. I didn't announce it, but we need a table. And for the table, I'll put the values of kt, values of x, which is mu b divided by kt, then w1, which will be e to the power x, w2, which will be e to the minus x, and then this cosine and sine, cosine x and sine x. And I'm going to explore this observables in three regimes. So when temperature is 0, when temperature is equals to the energy of interaction between spin and magnetic field, and when temperature is infinity. So what will be x if temperature is 0? Infinity. What will be x if temperature is mu b?
1.
1. Okay. And just for the comfort of drawings, I suggest to maybe, again, catch me if I do something wrong, but I'll put minus here. It will be a little easier, and we can correct things. And then if temperature is infinity, then this x will be 0. Okay. Now, what will be the weight factor for the first spin? So e to the power minus infinity will be 0. E to the power minus 1 will be 1 divided by e, so like 0.3, something like that. And e to the power 0 will be 1, correct? Now the second branch, e to the power plus infinity will be infinity, right? E to the power 1 will be e, like 2.7. And then e to the power 0 will be 1.
Wouldn't that be negative e? Because it's -1?
Or here?
For MB. Because you said, because if we put e to the -1.
So negative power means 1 divided by the same power, right?
Yeah.
What's question about this? It will be still a positive number, the small one.
Okay.
Same like 10 minus 1 will be 1 divided by 10. Make sense?
Yeah.
Okay. And I'm just lazy to fill this table. Maybe this data should be sufficient. So I'm going to erase this panel and try to just plot values from the table. So temperature goes from 0 to mu b to infinity. So it's KT axis. The another 1 over temperature or minus 1 over temperature. So we'll call it minus mu b over KT. So it goes from minus infinity, then to minus 1, and then it is 0. And our common sense forbids us to go to the right side of the image, but if we are crazy, we can just see what happens for lasers when systems are excited high, like to violate the Boltzmann. Now, I will need several points, and here it will be 0. Then I need to 1 over e, which is like about 0.3. Then I need 1. Then I need e, and then I need infinity. So in some sort, it is kind of logarithmic scale, but we are doing just quantitative. So I'm just going to put some points here. And let's agree that W1 will be red and W2 will be blue. So W1 at infinity starts with at 0. Then at constant, it has value 1 over e. And then at temperature equals infinity, it is the value of, we just put everything proportional to energy. Proportional to energy. We have this, or energy divided by mu b. Yeah, dimensionless. It goes here to 1, right? And we know that we are looking for variable x. It will go just as a regular exponential. Right? We are not allowed to look at the right, but basically it's an exponential function. Now let's look on the W2, which we will use blue color. So when temperature is 0 and x is minus infinity, yes, x is minus infinity, but we put here minus sign, so it will be infinity. When temperature is constant and x equals minus 1, it will be e. Right? And when temperature is infinity, it will be also 1. So I'm going to connect these lines. Yeah, I can do continuous line. And if you go to region which is forbidden by common sense, it will be just e to the minus x, right? So 2 exponentials. Now, if I want to practice the hyperbolic cosine, it means I just add together these 2 lines and then divide by 2. So it means I put the mean average point between these 2 points. Between 0 and infinity, it still will be infinity. Between e and 1 over e, it will be somewhere here. And here they coincide 1, so it will come through 1. And then it will go up. Cosine hyperbolic of x. Right? I'm not lying yet. Now, if I subtract the blue minus red, so infinity minus 0 will be still infinity. E minus 1 over E will be a little bit lower, and I need to divide by 2, so somewhere here. And 1 minus 1 will be 0. So it will go and then on the forbidden region, it will go this way. So it is changes the sign, same as our regular sine function, but it is instead of oscillating, it behaves different way because it's exponential. So this will be sine hyperbolic of x. And now how are we doing this time? Yeah. Now I want to divide this dot dashes by this solid black. So if I divide infinity by infinity, I will get 1. And I need to decide which color. I'm out of colors, but maybe I will do dual. Now, if I divide about half by about 1, so it will be about half, somewhere in the middle here. Maybe a little shifted to the towards 1. And when I divide 0 by 1, I'll definitely get 0. So the line will look this way. So of course, with computers in modern age, we can easily do it. And you saw it on the lab in MATLAB how one does it. But this line is minus tangential, and if we put this minus mu b, if we go from dimensionless to dimensionful things, we just flip the stuff, right? And then the dependence will be minus mu b, and then it starts growing and does something impossible in forbidden region, going to the positive values. But if we are restricted with equilibrium thermodynamics, the energy of this spin cannot be bigger than 0, because even at infinite temperature, in equilibrium, it will be probability 50 and 50 for spin up and spin down. So the energy will come to 0. And your homework, which will be derivative of this line in analytical form, and maybe do a graphic and analyze. So it will go as 0 initially, and then it will start growing. Right? Whew. Basically we are done. And you will see in your homework that the maximum will be at temperature equals infinity. So the function will be growing, likely, not going down, but growing. So also something goes up. But if we start to consider more than one spins, if we allow them to interact, the heat capacity will have a maximum and then will start dropping. And it will be a very specific temperature, which is critical for the material, which will be a signature for the material. So what we do right now can be projected to multiple spins if we forbid them to interact. If they are just silly spins that do not see each other, right? But if they allow to interact with some collective effects, then it will be the heat capacity will show maximum, and this maximum is a true challenge for pen and paper derivations as we practice right now, but it is a very typical problem for computation, which we will try to do in project in a collective way. What else? I think enough, right? So meeting is done. I'll stay here and answer any questions, and I'll count for like 1, 2, 3, 4 questions. If there will be no, I will disconnect, and everyone is welcome to disconnect as well.
And the homework is due Wednesday. I know you said possibly Wednesday, possibly Monday. Which one do you want it?
Let's give me suggestions how to make you happy. Maybe due Monday, but everyone who does it by Wednesday gets double credit. Okay, but double credit means like 200. You do not need a double credit to succeed in the course. Just if you want to create a safety cushion for the future. Okay.
Okay, the thing is that I cannot read the homework 1 question correctly because it's a little bit small. So can you type it and send us?
I will type it in the email, but okay. Basically take the derivative of the find heat capacity of a spin in a bath, right? Which means just derivative of the energy as function of temperature, derivative of energy over temperature, and then make a graph and provide some verbal explanation when it has minimum, when it is maximum, and why. So like 2 lines or 1 line of derivation and 2 lines of text. Make sense?
Yep.
Okay. Any other questions, suggestions? Okay. More questions 1. More questions 2. More questions 3. So meeting is truly done. I'm